Afternoon, everyone. Welcome to the Rewley Lecture and to the Sheldonian Theatre. The Rewley Lecture is the premier event for a benefactors program and provides an opportunity for us to celebrate our donor generosity and for allowing them to meet the beneficiaries of their support. This lecture is open to the wider Oxford community, and I can see that many of you are here today, so very pleased. And this is really an annual lecture where we get a chance to explore some of the biggest challenges facing humanity. In previous years, we have been joined by Dame Sarah Gilbert discussing the COVID-19 pandemic and Professor Sir Dieter Helm on climate change. Before I say a few words to introduce our distinguished speaker for today, I would like to say a few words about this very elegant building that we are holding the event in. Elegant and strong in design and marvelously rich in craftsmanship, the Sheldonian Theatre has admirably served for over 350 years as a dignified and superb setting for ceremonial occasions. Located in the heart of Oxford's medieval city centre, the Sheldonian Theatre is the principal assembly room of the university and the regular meeting place of the congregation, the body that controls the university affairs. All public ceremonies of the university are performed here. Now, a few words about the architect, Sir Christopher Wren. He designed this when he was only 32 years old, and he trained to be a professor of astronomy at Oxford. But his interest and passion lay elsewhere, and he got fascinated by architecture. To build this amazing building, he was inspired by the theater of Marcellus in Rome. Now, we all know the weather in Rome is a bit different from the weather in Oxford. So he needed a roof to cover the structure. Now, getting these long beams of wood was not easy because they were not long enough to cover the entire structure. So what he did was he collaborated with the professor of geometry to put in place a very novel grid design that holds this amazing fresco even today. And this beautiful fresco basically signifies ignorance being expelled from the university and truth descending upon the arts and sciences. It's really a very beautiful building. And we have our annual end-of-course ceremonies out here. And I'm very pleased that today we are able to welcome Laurence Moroney out here for this Rewley lecture. Before I hand the floor to him, a few words about him. So Laurence is returning to Oxford after a gap of 30 years. So welcome back. So Laurence, in a way, nothing has changed at Oxford. In a way, another way, everything has changed. So Oxford, clearly, after the COVID vaccine success, has really become a sort of leading university spot for excellence in innovation, entrepreneurship. And today, the topics of AI clearly is very linked to that area. Now, Laurence leads AI advocacy at Google, working to inform developers and those with non-tech backgrounds alike about the opportunities of machine learning. We are grateful to Laurence for giving us this time and sharing his expertise, and to Google more broadly for the continued support of the school through the Future Marketing Initiative. As an advocate for AI, Laurence encourages responsible use, but works to educate on the possibilities of AI systems and the tools and opportunities available so the developers are able to find productive uses of AI that are real, different, exciting, and have a positive impact on the world around us. Laurence described the current work happening in AI now as being on the cusp of a technological renaissance. As some of you may know, my own background is in artificial intelligence and computer science, and my academic research is focused on how business can increase the competitiveness and create growth through technological innovation. Adapting to AI offers both challenge and opportunity, And I really look forward to hearing Laurence's insights on how we can all best embrace AI, and hope you'll join me once again in warmly welcoming Laurence back to Oxford. Laurence, after his presentation, will engage in a Q&A, which will be chaired by my colleague, Professor Andrew Stephen. Andrew is the Deputy Dean for Faculty and Research, the L'Oreal Professor of Marketing at Oxford Side. And Andrew's own research predominantly focuses on how new technologies such as AI can benefit both businesses and customers. He led Oxford's AI Cross SDGs initiative and currently leads the Future Marketing Initiatives. Welcome, Laurence, over to you.
Thank you. And thanks, everybody, for showing up on this lovely evening into this beautiful building. So thanks for that beautiful introduction. I'm just going to get right down to it. So I'm going to start with this graph that I drew a couple of years ago. And this was a graph that I did where I took a look at the economic output and I averaged it across like a number of countries in Western Europe and North America since World War II. And you can see it was generally increasing until there's a cliff on the right-hand side, which you can imagine that cliff was the beginning of the COVID pandemic and the beginning of shutdowns. Now, it doesn't really tell you a whole lot because it's just generally going up. And like, how can we glean some intelligence out of this? How can we see trends in this? So what I did instead was I took a derivative of this graph where I said, okay, let's take a look at economic output as a function of the previous 4 years. So then we can see periods of sustained growth and periods of loss. And I deliberately didn't put dates on this one so we can start trying to guess what these are. Because you can see there's two pretty major plateaus here. And these are the two major plateaus that I've seen, that I've experienced during my career. This is the first of them. And this one started right around 1993 and ends right around 2006 or 2007. Can you guess what was the driving factor of that? Technology, but it was the advent of the internet. Right, so we'd had internet, we'd had like small scale internet, like between companies and between universities before that, but it was really right around 1993 with the advent of the World Wide Web, and then people being able to access the internet at scale at home, first by dial-up and then later by broadband, drove all of these new businesses that just didn't exist before then. Google, right? Who needed Google before you had an internet? Amazon, who needed that before you had an internet? Now these are two of the largest companies in the world. And it was a technological trigger that drove this. It drove this revolution. The second one started around 2008, 2009, and ended with the beginning of the COVID pandemic. Can anybody guess what that one was? It was the mobile-first economy, right? So when Steve Jobs went on stage and said one more thing and introduced the iPhone, he revolutionized the world. There were mobile phones before that, but that was the beginning of smartphones being internet connected, being affordable, and giving developers the access to build applications for them. So think about what the world looked like before the mobile phone. And we have a joke inside of Google where it's like, once upon a time, the older folks amongst us will remember that we said, you never talk to strangers on the internet, and you never get into a stranger's car. But now, we will literally summon strangers from the internet and get into their car. It's called Uber, right? It's one of the ways in how the world has changed. But again, these technological triggers have been massive drivers of the economy. And one interesting fact from the right-hand side of this graph was that at the beginning of the pandemic, 2019, 2020, in the UK alone, the Apple side of the mobile economy added 600,000 jobs. While many jobs were being lost, just Apple side of mobile economy, they published their figures, 600,000 jobs. And that's everything from software developers to administrators to enabling drivers, delivery drivers, all of those kind of things. And while most other industries were shutting down, furloughing, laying people off, that mobile industry was continuing to grow greatly. So technological triggers like these can be massive drivers of the economy. But the bigger one is coming, and that is the one of artificial intelligence. And don't just take my word for it. Here's a couple of stats that I wanted to share with you. The World Economic Forum did a Jobs of Tomorrow report where they started looking at the jobs of tomorrow, plus 37% in data and AI, plus 34% in engineering and cloud computing. And then adjacent jobs, people in culture, product development, sales, marketing, all growing drastically. Now, one thing that I do have to say, a little story I want to share, is that this country, the United Kingdom, has been one of the best countries at being forward-looking in these things. If I go back to this diagram, I graduated university in 1991, right into the biggest recession that the British economy had seen in many, many years, and I graduated and was unemployed. But the British government at the time, they actually started an initiative back in 1992 to create a consortium, an AI consortium, where they were going to bring in 20 people. They were going to build these 20 people up to be AI experts, and then these people would go out into industry and help industry to see if that could help the UK economy grow. And this was in 1992. Unfortunately, it failed. We've probably all heard about the AI winter. The technology just wasn't there yet. But that foresight was there in this country, and it is still there. Even today in the House of Commons and the House of Lords, there's a group called the All-Party Parliamentary Committee that what they're doing is they're getting together, going cross-party to try and figure out how we can use AI in the United Kingdom to help everything from the National Health Service to the private sector. And I'm an advisor to that group, and I have to admire what you are doing in this country, and just really thank you that as a leader and as a global leader, you're doing some great things. Another report was from Forbes, and they were looking at the global ML market and AI software revenues growing. And you may have seen that this is a slightly older report, that the CTO of IBM just last week estimated that it could be worth up to $4 trillion, the AI economy, within the next 5 years globally. So these are the kind of things that are out there. This is the opportunity that is out there. Hopefully someday in the future we'll be drawing a graph like this, and it'll be a much bigger plateau and a much longer plateau. And countries like the UK are the ones that can take advantage of that. But we also hope it will be a global thing. But what I do want to talk about first is hype. And one of the things that can damage perception of a technology, and then if the perception of the technology doesn't get beyond the hype cycle, a technology can fail. And with AI, or any hype cycle will begin with a technology trigger that's a new thing that comes on the scene, like the internet or the iPhone, and it will already be behind what's called the peak of inflated expectations. Now let me tell you about a failure. Has anybody heard of Google Glass? How many people have a Google Glass? Nobody. I got one. But when you think about Google Glass, right, and you think about that purely from the point of view of hype. So the Google Glass burst on the scene like in the early 2010s, and it was this device that you could wear and had a little screen that you put in front of your eye, and this little screen could show you notifications, and it was actually quite cool. But it was very, very misunderstood. Movie theaters moved to ban the use of Google Glass in the movie theater because they were afraid that people would film the movie with it and it would become a pirated movie. However, if you actually ever tried to use a Google Glass, the battery would last about 15 minutes if you were making video, and it would get so hot it would burn your ear. So nobody was going to steal movies with that, but the narrative was out there that they would. And as a result, this false narrative, this negative narrative around it, was one of the things that condemned it. We could never get beyond that narrative and make Google Glass to be a success. But if you think about what Google Glass was all about, how many people are wearing an Apple Watch or have a smartwatch? I bet it's a lot more than none, right? But it's exactly the same thing in just a different form factor. It's a thing that drives notifications to you. It's a way that you can get notifications and see what's going on without actually looking at your phone. And that was part of the point of Google Glass. So this is like when we will succeed with any technology is when we drag it beyond that peak of inflated expectations and land in this spectacularly named trough of disillusionment. And that's when we've gone beyond the negative stories, we've gone beyond the hype, we've gone beyond all of the false narrative that's out there, and we understand what the thing is really all about. And when we look at AI today, unfortunately, with AI, we were kind of here until the release of ChatGPT, and then we went back here. There's all of these stories about it taking jobs. I arrived in Heathrow this morning. I got an Uber here from Heathrow earlier this morning. The taxi driver asked, or the Uber driver asked what I was doing. I was mentioning I was doing this lecture. I was doing it on AI, and his instant reaction was fear. Is it going to put me out of a job? Is it going to kill us all? Is it going to do all of these things? And it's like, and this is classic hype cycle stuff, classic peak of inflated expectation stuff. But if we can move beyond that and understand what a technology is all about, and the mundane side of the technology, then we can start being creative and doing magical things and move up towards productivity. So let me give an example of that. So AI is part of computer science, and computer scientists and developers, our bread and butter has always been explicit coding. And explicit coding is when you want to do something, like we've all probably seen this game where, you know, it's a breakout kind of thing, where it's like everything that happens in the game, there's a rule associated with that. The programmer has to figure out that rule. What happens when the ball hits the brick? Which direction will it go after? How will the score increase? You figure out what all of those rules are and you express those in a programming language. You know, so, but the key to this is that the human being is figuring out those rules. The human being is expressing them in a programming language, and then the human being is giving that programming language to a computer and turning that into a game. So that's explicit coding, and that's how software development has been done since the dawn of time. And this is the traditional programming paradigm I like to draw like this, where generally it's like you got a whole bunch of rules, like the things I just mentioned for the breakout game. They act on data. Data could be the location of the brick, the location of the ball, the score, all of those kind of things. And the program will give you answers. And the answer will be, the score is going to go up by this, the game is over, those kind of things. Machine learning and the machine learning revolution is very different, and it just turns this on its head in a very simple way. Now, let me give you an example. Say, I'm going to go back to the Apple Watch thing again. These all have activity detection. Fitness is one of the core things that it's all about. So, for example, if you use it for fitness, you probably want it to detect what your activity is right now. So say, for example, you're walking. Now, how would you write explicit rules to determine if somebody is walking? You might say something like, well, if they're walking less than a certain speed, if they're moving at less than a certain speed, then they're probably walking. Right? So say less than 4 miles an hour, then they're probably walking. And then you go, okay, how can I detect if they're running? You go, okay, well, if their speed is less than a certain amount, they're walking, otherwise they're running. You know, these are kind of rough rules that we could figure out. And then we say, okay, what about biking? I like to bike. Well, if their speed is less than that amount, they're probably walking. If their speed is less than a higher amount, they're probably running, otherwise they're biking. Crude rules, but they kind of work. But then we say, what about golf? Uh-oh. How do you determine the rules for golfing, right? You know, that kind of, when I golf, I'm a really bad golfer. I'll hit the ball, walk 2 yards, hit it again. You know, when I play with people who are good golfers, they'll hit the ball, walk 100 yards and hit it again. You know, those kind of things. It's just, it's infeasible. The amount of rules that you would have to write, the amount of thought that you would have to put into doing this kind of thing if you're trying to express this in rules, it's next to impossible to do. And that's why before machine learning and AI, you didn't have smart activity detectors that run on your wrist. So how do they work? Well, if I go back to the programming paradigm that I was talking about, you got rules coming in, you got data coming in, and answers will come out of that. What if we flip this around a little bit and we do it this way? What if we put answers in along with the data and we have the computer figure out the rules? We say, okay, well, how would that look? Well, if I go back to what I was just talking about, now I have a sensor on my wrist, like the Apple Watch or other things, and this is gathering a whole bunch of data, and I'm not trying to figure out what that data is all about, but I just say, when the data looks like this, I'm walking. When the data looks like this, I'm running. When it looks like this, I'm biking. And when it looks like this, I'm golfing. And we say, okay, can we have a computer figure out how to match this data to this label and figure out the patterns behind that? Because that's what computers are very, very good at. They're very good at number crunching. There's no magic going on here, and it's a case of, yeah, we can do that with a computer and say, you know what, when these ones are set, these ones are only set this way when they're walking, these ones are only set this way when running, biking, or golfing. And now a computer has learned from the data how to distinguish walking, running, biking, and golfing. And that's where the term machine learning comes from. Before I'd heard of machine learning in this way, you tend to think of robots sitting in a classroom, you know, that kind of thing as being machine learning, and it sounds scary, but it's not really that scary. That's all machine learning is it's getting lots of data, figuring out the patterns in that data, and then being able to use that to come up with solutions that weren't previously possible. Now, this is a silly example that I've given. Let me now turn that into a real-world example. It's diabetic retinopathy. So this is one of the fastest growing causes of blindness globally. About 400 million people plus have been diagnosed with diabetes, and you can see in this chart here there's so many of them, and it can lead to blindness. So one of the important things here is that the interesting thing about diabetic retinopathy is it can be prevented with early diagnosis. It is, you know, it is hard to get an early diagnosis in some parts of the world because there's such a shortage of doctors. And we worked in India in particular, where we discovered there was a shortage of over 120,000 eye doctors, and as a result, 45% of patients had some loss of sight before diagnosis. And that's the crying shame of this, is that this is easy to avoid. The problem was we didn't have enough people who could help avoid it. So we thought, okay, what if we start scanning retinas and we hire a whole bunch of doctors at Google, and we have these doctors look at the retinas and give us a label. And we broke it into 5 labels, from no diabetic retinopathy all the way up to proliferative diabetic retinopathy. And a doctor who's an expert in looking at retinas will see things like hemorrhages in it, and they will label it appropriately. And now we have a data set, and we've opened this data set so anybody can use it, where we have, I think it's about 35,000 of these scans that have all been labeled. And from that, we could build a neural network that could do exactly the same type of pattern matching that I just showed. It was like saying, okay, well, when the eyeball has this is no diabetic retinopathy. When it has this, it has severe retinopathy. And have a computer figure out the patterns. Now, notice the difference here. And this is really important. When a human doctor is going to be figuring out those patterns, they have a set of rules in their head that they're following. It's got these hemorrhages, it's this color, those types of things. But they learn those rules as part of their profession. But when the computer's trying to do the pattern matching, it's not bound by those rules. And that's really important, and I'll get to that in a moment. But what ended up happening is the first time we built this, we found that the score of this thing was that it was 95% accurate, where the average ophthalmologist is 91% accurate. So please note here that I'm not saying that this should replace an ophthalmologist. This is the kind of thing is how we can scale ophthalmologists much more effectively, because in some parts of the world there were shortages of them. And we continue to improve on it, and I'm sorry, it's taking a little bit to download. And so, but by 2016, we were on a par with a general ophthalmologist. By 2017, we're on a par with specialist ophthalmologists. And again, it's like just because we got lots of raw compute power to start matching the retinas to the labels. But now here's where it gets interesting. Now, looking at a retina, another piece of data that we had about each patient was their birth-assigned gender. Now, if you look at a retina, how can you tell if that's a retina from a male or a female? You can't, right? And if you follow the rules that an ophthalmologist is trained on, to see, like, here's where the blood clots are, here's where hemorrhages are, there's nothing there that you'll be able to tell if that's a retina of a man or a woman. And so if you were to look at it, it's going to be a coin flip. It's 50-50, or close to 50-50, depending on the population split. But when we did it with this one, we actually got it to be 97% accurate. So again, from just matching those patterns, the computer was able to derive the rules about this is a retina of a man or this is a retina of a woman. And now we can start saying, by having this technique and by using this technique, we can start creating whole new classes of application or doing whole new things that weren't previously feasible or possible. Now, determining if somebody's a man or a woman from the retina, of course, isn't one of them. But when you start understanding that data can be used in this way, and visual data in this case can be used in this way, you can start coming up with solutions to problems that weren't, as we said, previously feasible. So another one that was like, I know it's downloading it. My personal favorite one is actually the person's age. So when we also had the data of the owner of this retina, what their age was, and when we trained the model against trying to predict their age, it had a mean average error of 3¼ years. If I were to ask everybody in this room to guess my age, and I averaged it out across all of you, I bet, and you're seeing me speak, you're hearing me speak, I bet you would be off by more than 3½ years. But this model, from just looking at a retina, had a mean average error of 3¼ years. So things like that, like these kind of discoveries were made possible by that technique alone. And there's nothing special about it. It's just taking a look at data, it's writing fancy computer code that's able to match that data to labels, and then being able to make interesting discoveries like this one. So my goal and my job is to get people into this trough of disillusionment. Right? I'm professionally paid to disillusion you, so it's quite the interesting career. Because when you get there, that's when you can start really applying yourself to be able to rise up towards productivity. And you don't need to be a computer engineer or a software engineer or a computer scientist or anything like that to be able to do this. We're moving into an era where it's easier than ever to be able to do this yourself, and I'll be talking about that in a moment. And I want to tell one story that my friend Laurence and Tommy are in the front row here, and I worked with them on a project called Stargate AI. And what we did with Stargate AI was that we wrote an AI system to kind of generate scripts from the TV show Stargate, and we brought the actors from the TV show together to do a reading of these scripts, and they produced a lot of gobbledygook, and it was a lot of fun because there wasn't that much data compared to what you'd train a large language model on, and we had a lot of fun doing them. But one of the things that came out of that was one of the actors in the show, his name's David Hewlett. You know, at first, he was behind the peak of inflated expectations. He was scared of AI. He was like the same as everybody else, reading all the stories of how terrible it is. And then he got scripts that were produced by an AI that were far inferior to those that would be produced by a human. But then the light bulbs went off in his head. And one of the things that he shared with us was that as an actor, he's not an A-list actor. He still has to go and audition for jobs. And sometimes it's hard for him to prepare for an audition. He might be going to, for example, audition for a horror movie. And you know, how does he prepare for that? He can't afford to hire a writer to write scripts for him just for him to prepare. But when he could get an AI to write these scripts for him, that he could prepare. Now suddenly, this person who's not an AI person, who's an actor, is bringing his domain knowledge of acting to this realm, ideating something that he could potentially build a business around. He was in that trough of disillusionment, and he could rise up to productivity, and he could build a useful product for actors everywhere. So that's where we're at with the computer industry, with AI, with machine learning and all that, until recently. But then along came our friend ChatGPT. How many people here use ChatGPT out of interest? Yeah, just about everybody, I figured. You know, so ChatGPT, let me talk a little bit about it, because this has driven us backwards in the hype cycle. And when I look at ChatGPT, I just grabbed a few random news articles, and this thing like, you know, it's being used by cyber criminals to generate scams. Can it build an entire brand? Apple blocks use of it because they, you know, they worry about the harm. You know, retailers see promise in it. Are lawyers going to be laid off? All of these news stories, if you just search for ChatGPT, come up. My personal favorite one was this one, where apparently there's a newspaper called the Olive Oil Times, and in the Olive Oil Times they talked olive oil with ChatGPT, which is, like, I thought, really fascinating. But that's put us all the way back here. We're now back behind the hype cycle, because now there's this big mysterious entity called ChatGPT that's able to do amazing and wonderful and magical things, and most people don't know how it works, and fear leads to fear. You know, it leads to us being afraid of it and pushing us back beyond the peak of inflated expectations. So I'd like to talk a little bit about what it really is and how it all works. So the T in ChatGPT stands for transformers. GPT is generative pre-trained transformers. Now all transformers are, if you remember my pattern matching that I was talking about earlier on, are a way of transforming one piece of text into another, or having a computer learn how one piece of text gets transformed into another one. So answers and data in that I was talking about, well, the data is a sequence of words. The answers are just whatever follows that sequence. And you think, man, that doesn't really make any sense to me. And I say, okay, what if I give you this sentence? If you're happy and you know it. Clap your hands, right? Does everybody say clap your hands? Does anybody say something different? Okay, well, my wife is from Hong Kong, and she swears blind that at school she learned, which is much nicer, if you're happy and you know it, you clap your hands. Right, which is a description of your reaction as opposed to a command. But if you think about it as a sequence of words, if you're happy and you know it, clap your hands. That what you'll start thinking about is, like, you see this sequence if you're happy and you know it, and what a computer is going to do is going to match that, for the most part, to clap your hands, because most examples that it has seen in text will say clap your hands, but maybe a few of them will say you clap your hands. So a transformer learns that sequence of one set of words being transformed into another. So whenever you're talking with ChatGPT, all you're doing is you're typing in a bunch of words like, say, I don't know, give me a haiku about my dog, and somewhere on the internet there are many thousands of sentences that look a little bit like what you've done. There may not be an exact one, but there are some that look like it. And then there are sentences and words that follow that. And ChatGPT, because it has a transformer, is predicting and calculating those and outputting them right back at you. There's no intelligence going on there other than the artificial intelligence of making it look like it's actually smart, but it's just, some people call it a stochastic parrot. You know, it's just repeating sequences that it has actually learned. You know, so again, your sequence of words comes in, whatever follows that is out. Machine learning has learned the rules that map one set of words to another, and then you know, those rules are the intelligence of the system. The GP in GPT stands for generative pre-trained. By pre-trained, it means we've looked at all of this text that's on the internet, all of this text that was made available, and we've looked at how the words in that sequence to the subsequent words, and then the generative part of it is like, okay, now you can start predicting next words in a sentence, like clap your hands. This was originally invented for machine translation. Now let me give you one example of that. I don't have a slide for it, but anybody here speak Gaelic? Oh, there's one. Okay, nice. So if I say, "Is my anfichtov leis na garachig," can you translate that? Okay, so "Is my anfichtov leis na garachig" is an Irish proverb that means the raven loves its chicks. What do you think that means? Can anybody guess? The raven loves its chicks. Okay, so with machine translation in the past, you know, what you would have is you would translate word for word directly. "Is my anfichtov leis na garachig" becomes "the raven loves its chicks." But that doesn't really make any sense, and that's why machine translation was really bad. But what the meaning of that phrase, "the raven loves its chicks," is, as Shakespeare said it far more beautifully, beauty is in the eye of the beholder. So now a machine translation system with a transformer would see those Gaelic phrases, and instead of translating it literally into "the raven loves its chicks," it could translate it into "beauty is in the eye of the beholder." That's what a transformer model was built for, and that's how GPT arose. And somebody just said, hey, we don't have to just use this for translation. We can use this for generating new text by pre-training on existing text. So you've probably heard of the concept of a prompt, and the prompt is the existing text, the output, and like the clap your hands, the completion is the prediction of that. So for example, if I go to Bard, which is Google's version of ChatGPT, and I type "if you're happy and you know it," it'll output something like this. So these types of models, these transformer models that are grabbing all the headlines, that are scaring the life out of people, that are making people fear that jobs are going to be lost, you know, they're not really that scary. But the one piece of advice I would always give is that while you may not lose your job to an AI that's created with these, but you might lose your job to, if you're not using them, to a human that is using them. So for example, in the good old days when accountants only had pen and paper to work with, you know, and then computers came along with spreadsheets and accounting software, the accountants that used the spreadsheets and accounting software would put the accountants who don't out of work. And that potential thing can happen with these types of tools. They are so powerful. So one of the things I would say, some advice around these is just to remember, the first thing is they are generative, which means they make stuff up, right? They're not a fact-based database. You shouldn't really use them for fact-based searching. I'd always say, like, if you want to learn a cookie recipe, you can use ChatGPT. If you want to learn Jamie Oliver's cookie recipe, don't use ChatGPT, right? Because it's going to make stuff up. So they're excellent at finding patterns in text and then giving those probabilistic next outcomes. So things like storytelling or other creative work, or analyzing creative work, or lists or other opinion-based content, drive an agenda for a meeting, those kind of give me a plan for doing my homework or my fitness, write code, those kind of things. But always remember that they're generated based on these probabilistic outcomes, so you cannot trust them as fact. A lot of people made that mistake. Even Google have made that mistake. You probably saw we put out a TV commercial back in February where we had a factual mistake in the TV commercial that came out of our large language model, and our stock dropped 10%. And we're a big company, and 10% is a lot, you know. So it's one of those things that you have to be really, really careful about. Hopefully that won't impact you. But the really big thing about this is it is that potentially new compute platform of the future. Today, the world has 30 million software developers, and the biggest companies in the world, the Googles, the Amazons, the Microsofts, everybody else, are really built on the work of those 30 million software developers. That's a very small number of people for the impact they have on the global economy. This thing can be the new compute platform of the future, and anybody can be able to use that to create new solutions. Can you imagine what the world would look like if there are 300 million software developers? And that's part of the strategy I drive at Google. I call it the 3-30-300, because today there are 3 million developers in the world who can do AI. there are 30 million developers who can code, but tomorrow, 5 years from now, there will probably be 300 million people who are able to build some kind of application that other people will use, and they'll be building it using these large language models. So why not start today? Why not let that be you? This is let's get beyond the peak of inflated expectations. Let's get into the trough of disillusionment and be able to do that kind of thing. And finally, I want to show you the picture. This was the very first computer that I used. This computer was called a VIC-20, and if you look really closely, it says it has 3,583 bytes free. Right? Not kilobytes, megabytes, or gigabytes, bytes.